It looks like it turned off, so apparently that was it, the juice. Nope, wait, nope, it's coming back again. All right, so right now, assuming that all of your eyes are young and good, it's giving me position to the ceiling, now to my hand. I'm going to measure the distance going that way. So when the cart is here, it is roughly 55 centimeters away. Yeah, close enough. 61 centimeters. If I'm within 15 centimeters, it's going to mess up there. All right, so I'm going to let go. I'm within 15 centimeters, which means part of what it's going to measure is going to be garbage, but that's okay. Finding the acceleration in this method, just so long as you don't curve fit to the bad data, it's okay. Also, I want as much good data as possible. Come on. So I want as high a sampling rate as it will go, and 50 is the highest that it will go. All right. So there's a green triangle down there that's going to start the recording. I want to make sure the cord's out of the way.
You're going somebody to start the recording so that you can.
Precision is not crucial.
Well, you usually have your other hand to stop it from hitting the bullet.
Oh, yeah. Good. Thank you. As somebody was thinking. Also, this string should be as parallel to the track as possible. All right. Let me know when you hit it.
Right. 3, 2, 1, go.
All right, stop it. All right.
Bullet, stop.
Graph, show graph 1. All right. How low can you see that? All right, so the part when it's actually accelerating the way we want it, it's that part of that parabola here. Then I stop it, and the rest of that is garbage, because that's the slowing down phase over here. So I need to curve fit this part over here where it's going up. So what I'm going to do, I know the first potential data points are potentially garbage. It's doing this and then do something like that. I don't want to get too close to the edge here, but I'm going to take a section in the middle and I'm going to highlight it. Come on. Apparently I have to press. There's no stylus on these, is there? Thank you. Ah! All right, I'm going to do this a different way. Graph, graph options. Cancel. I want to go to from about 0.5 seconds to 1.1 seconds. So graph options. LabQuest 2 is much easier in this respect. So 0.5. 1.1. All right, so I've basically zoomed in on one particular section of the graph. It is still curved in a parabola. and now I'm gonna curve fit it. So I go to Analyze. Apparently it doesn't like that.
Sorry.
Curve fit, position. Now it's gonna bring me, it automatically does a linear fit. I'm not expecting it to be linear, I expect it to be a quadratic fit or a parabola. So I do my drop down here, I click on quadratic. And I don't know if you can see, there's a red line and a black line, and I suspect you can't see it, but the black line is right on top of the red line because it is an incredible fit. Down at the bottom is called RMSE, that's root mean square error. You want that as close to 0 as possible. And so the measure of the error in the equation, 0.000323112. So that's tiny. All right, so the equation it gives us, I'm going to retranslate. So my position is 41342. 0.41342 times time squared. Now it's giving me y and x, but I'm translating to what's actually happening here. B, negative 0.021477. Negative 0.021477 times time, and then plus 16839. Now, right now, I imagine that for a number of you, or possibly most of you, all of you, these just, they're numbers. What do they mean? All right, so that is my A here. That is my B, and that is my C. Physically, this is a measure of my initial position. I started out roughly 16, 17 centimeters in front of the screen. This is a measure of my initial velocity. Should be somewhere around 0. This is not the acceleration, but it's a measure of the acceleration. The units here are meters per second squared. The units of this are meters per second, and the units of this are meters. Probably the biggest mistake students have made on this is they look at that, they see units of meters per second squared, and they go, oh, that's my acceleration. It is not. This A here, if we wrote down the official formula, that position is equal to 1/2 AT squared plus VIT plus X initial. That's the official formula. Hewitt doesn't go into that. Hewitt gives you that, the 1/2 AT squared, and Hewitt gives you the VT. One of the videos, I combined the two. But the important thing to pull here is that this coefficient, this number in front of the quadratic term, is half the acceleration. So you would take that and multiply by 2, and we got an acceleration of 0.82684 meters per second squared. And we had predicted 0.88. Not too bad. Better. But we can do even better. Oh yeah, that look of excitement that you have, that's, I want to capture that. That dramatic pause there was for questions. Any questions? Now, we assumed that the entire force that was accelerating this was the mass of was the weight of whatever was hanging. We ignored friction. We ignored a lot of other things. The way that you would deal with that is you would do several trials. Make sure that the total mass stays the same. And you're going to plot acceleration versus force. You should get a straight line. And the slope of this would be 1 over the mass. So this is one where you get acceleration versus force, and you would try to find the mass. So this is mass constant. That's not the title of the graph. That's just a comment. And the way you do that, because remember the total mass is what's on the cart, plus the cart, plus what's down there. So you start with masses on the cart. You run your trials. Then you take a cart from here, and take a small mass from here, you put it onto that, and you do the experiment again. The total mass is still the same because all I'm doing is transferring mass from the cart down to there. The total force is changing, but the total mass stays the same. And then I could test to see if I held the force constant under the mass and acceleration change. And to do that, to keep the total force constant, all I have to do is just keep that the same and just run my trials, put mass on it, do it again, then add another mass, do it again, another mass, do it again, and so on. Now, presumably, you know where this is leading. I'm hoping. Or if not, that's okay too, because I'm about to tell you. We're about to do this lab. Yes. Any questions before we wander down there and do the lab? You about to ask a question?
Just thinking, I need to ask a question. But you think that maybe.
All right, while he's thinking. I guess I can stop.